Thanks for having me here, first of all. Let's start with that. I just got to Australia about 6 months back to start a PhD. It's quite different with respect to what I'm doing a presentation on. But in some ways it's the same. You're working with subsystems that will be operating on off-Earth surface environments, and you're trying to understand how the environment plays a role in the actual performance of the system. So coming to the topic of today, it seems quite a mouthful, but basically what I'm trying to do is understand if ever we're trying to pick up regolith, which basically is, well, by one definition, between 30 to 40 micrometers diameter particles on the Martian surface. If you're ever trying to pick them up using pneumatic means, which basically means using a puff of gas, how exactly would that happen on Mars with respect to, if you were to compare doing that on Earth? What's different over there? Well, the ambient pressure, the temperatures, the gravity environments, all of these play a role somewhere or the other. And my work is to understand how exactly one can model these things without having to go there and then realize that a lot of the work that was done was futile and we should have designed our systems in a better way. So that's primarily what the topic is, to investigate granular flow in fluidized environments. If you're using a pulse of pressurized gas, and you're trying to just force up some amount of regolith up, you can relate to a vacuum cleaner, but just that vacuum cleaner, you're sucking things up, whereas over here you're trying to force the gas which is stored on board the spacecraft through a very narrow opening, and that's basically what it's doing, is it's interacting with the regolith on the surface and then scooping it up. It will get a bit more clearer as I proceed. So the work was done well amongst three groups of people. There was the academic supervision, which was done by Angelo Savoni at TU Delft. He took care. So while I was at Ames, I was actually working on something else, completely different from this topic. But I realized that I have to finish my master's from Delft, and they had very specific requirements from their department. And this was basically a child of that collaboration between Delft and NASA Ames, and also Honeybee Robotics. So the three groups basically were the academics from Delft. There was the science coming from NASA Ames, primarily from Christopher McKay, who's an astrobiologist, quite renowned within NASA, who's worked on a lot of missions that have gone there. And also from a subsystem development company, an instrument development company known as Honeybee Robotics, who has a heritage, who have worked on different sample acquisition as well as dust removal instruments that have flown to Mars. So that's basically the supervision that I got from these three different groups. And the way I try to put forth today's talk, so this is coming out from a master thesis presentation, so I'll try not to touch on everything because it'll take a little more time than that. But I'll just try to address all the things that I looked at, and it could be maybe useful to some undergraduate students that when you're trying to do a thesis with another organization, not people just within your university, but people outside, you have to ensure that how the requirements from the university have to be met, and at the same time requirements from the scientists or from the engineers have to be met. So if you're one of those guys who feels that your thesis should be at some point of time useful to people and not just to yourself, this might help you. So, basically touching on three quick points: the scientific objective, why is it exactly that we want to get hold of samples on the Martian surface and eventually bring them back. The design of the subsystem, which is basically driven by these scientific requirements, and at the end the academic requirements, what exactly would the supervisor be happy with. So coming to Mars sample return, well, we have international bodies that sit down every once in a few years, and they basically refurbish and then they revise the documents and they try to understand why is it exactly that we want to get samples back from Mars. Well, firstly, why Mars? Why are we interested in Mars? So just three crucial points. The first 700 million years of Earth's history is quite similar to what the Martian history was like. That's basically the time frame within which life originated on Earth. And a lot of that is lost because of tectonic activities on Earth. And it is believed that it is well preserved on, within the Martian surface. Now, to what depth do you have to get to achieve those samples? That's a different story altogether. But basically, that's the first justification that why we want to go to Mars. And in a lot of ways, Mars has an atmosphere, it has cluster characteristics. So certain presence of biosignatures one has already foreseen to be able to capture through these samples. And it's relatively close to Earth, so whenever you discover something from one mission, you can quickly, relatively quickly, you can send another flurry of missions that basically adapt to whatever first discovery was seen, and then eventually you have ongoing missions that can actually work upon the first mission, and then you can achieve certain goals, depending on whether you're trying to do science or trying to colonize or whatever. So in that sense, from a proximity angle, it's advantageous to go to Mars. And so you go to Mars, we've been going to Mars, but why bring samples back, given the fact that that just tremendously increases the cost of the mission? It has been seen that most of the instruments that are sent onto Mars, it's very quickly understood that they have limitations. There are certain things which you cannot achieve with instruments on board the spacecraft that are flying there. Some of them being you're trying to do stable isotope tracing, you're trying to do life detection, which is one of the biggest goals, scientific goals. It becomes very tedious to try to achieve all of that within physical constraints and also power constraints on Mars. And also, it has been noted that the amount of publications that we have done from meteorites, Martian meteorites that were found on Earth, is actually more than all the papers that were published from the work that had been done on spacecraft. And also, once you have the samples on Earth, you can keep them, share them with the international community, and as technology grows, your understanding of the science that needs to be used to curate these samples or to characterize these samples will also grow. And that's been seen with the lunar samples which we brought back. So, and also the challenges. So, if at all we're trying to understand Martian regolith, we do have lunar regolith, but we do not have a lot of samples from Mars. And one needs to understand if it is toxic, you need to characterize it. And dust in itself creates huge problems for spacecraft and landers and any extravehicular activity on anywhere. Could it be Mars, it could be Moon. Any moving parts, regolith gets within these small cracks and joints, and they reduce the life of machines tremendously. This was seen during Apollo, and it's something that we still do not understand how much regolith, how it actually behaves, especially in reduced gravity, temperature, pressure environments. So all of this, what I'm giving you, is the first part of the justification, the scientific justification which is given, that why would one want to go to Mars, bring samples back, and on top of that, why would you want to understand how these regolith behaves. So a rough figure which scientists put across is about, they say, give us about 60 grams of Martian dust. Now this figure has come out of a lot of trade-off done between science and technology, where they try to look at the amount of power that needs to be put in to lift off from Mars to bring samples back onto Earth. But even 60 grams, it sounds like a very small amount, but it's turning out to be a very expensive affair to bring back samples. And also the advantage of collecting regolith or finely loose grains from the surface is that it lets you sort these particles for doing X-ray diffraction and X-ray fluorescence studies. So just to give you an idea, this is just one of the sample return architecture. As you can see, you fly to Mars, you use a sky crane very similar to what the Mars Science Laboratory had used, and then you land a lander onto the surface. And I don't have a pointer, but basically what I'm trying to refer is to this particular phase sitting over here, that once the lander sits there, my entire work is focused on that particular part, where you're trying to acquire samples within the reach using scoops, drills, pneumatic efforts, and then eventually store them in that white canister, which then makes itself upright, and then you have a Mars ascent vehicle which launches off from the surface and then brings the sample into an orbit, and it rendezvous with another orbiter, and then eventually brings the samples back. Now within this, there are some critical technologies that haven't been developed. The most important of them being the ascent vehicle. It's called the Mars ascent vehicle. So in the recent report, which was I think last updated in September of last year, so there's a group called MABAG, which sits in NASA JBL, that just tries to understand and reiterates the importance of developing certain technologies and brings the technology readiness levels with the TRLs up. So that's one thing that's being looked upon, and also sample acquisition. That's another thing that I'm focusing on, is also being mentioned in that document, as we haven't understood how to develop drills, sample acquisition systems, to be able to acquire samples. And it's not as easy as it is over here. You need to send a universal sort of an instrument that can deal with different types of regolith, different types of rocks, and it's a huge conundrum of problems. So one has to actually just focus on one particular area and try to raise the readiness level to an extent, and just hope that maybe one day your instrument will be chosen and be developed and then incorporated into a mission. Having said that, the technology that I'm working on with Honeybee Robotics happens to be a secondary sample acquisition system. It already is foreseen as not being the primary acquisition system. Well, it could be if the main objective of that particular mission, if it's too light a lander to not have enough weight on it to support a drill, it could be the primary acquisition system in itself. But it's being floated as a secondary acquisition system. It basically means that you either have a drill and scoop, or drill or scoop flying, and then you also have this particular technology. So I'll quickly come to then what exactly we're trying to do. So Honeybee Robotics, I think they were here, Chris Zachney from Honeybee Robotics was here, and there was an off-earth mining symposium in which he gave a talk, I think last year.
He's coming again this year as well.
And he's coming again this year as well. And that's how actually I came to know about UNSW. I was actually watching all the videos and I saw, oh, they actually work on this area over here. But he, I think, already presented a slide on this particular.
Not so much in Canberra.
Not so much in Canberra, yeah. But well.
Also Regolith.
So here's what's happening. You have a lander that basically is a stationary platform that sits on the Martian surface, and the lander will have footpads. These footpads are being designed to have hollow tubings within them, and the idea is, as you can see from the figure on the right, very intuitive in that sense, that you have ports and you have an inlet to be able to force in gas. Now, where is this gas coming from? Now, that's an advantage of this system, is that it uses the leftover propellant which the lander uses to land. So every time we fly a lander to Mars, or actually anywhere, you always carry an extra budget, you carry a margin. And once it sits there, it's normally vented out into the atmosphere and it's not really used. So this particular design architecture, by no means being the final design of existing system being designed, but one of the candidate designs, actually uses that residual propellant. And that residual propellant is normally an inert gas, so it doesn't really react with the regolith, which is important. You don't want to use something that quickly reacts with your samples, and then your sample is basically useless. So it normally uses either helium or nitrogen, which is a common gas thruster. And that's basically what you see through the red arrows that's flowing out and flowing in through these lander legs, and then eventually being thrusted out through the outlet, and then eventually creating a path of least resistance for the particles to actually be lifted up. Very similar to mining efforts on Earth as well, underwater, where you actually use gas to force up particles. So that's the basic ideology. What is being done is you're not using many moving parts. There's just probably 2 balls involved. You're not using any drills or scoops which require actuators. For a sample return mission, the highest thing is redundancy, and the redundancy is driven by the actuators to a high level because they have a they have a risk of failing. So you want to reduce the amount of actuators that are actually being flown. And this actually came from another discussion that I was working on with Chris. So Chris is the head of the exploration group at Honeybee Robotics, and he has a PhD in Mars drilling. So one of the very few people in the world who've actually looked at off-Earth sample acquisition to that detail, and he's been working with Honeybee Robotics many few years. And as a graduate student, I approached him, and you reach a level where you think that most of the problems which NASA is facing or anybody else is facing is going to be like real high technology, state of the art. You'll have to do things which look really difficult. And I looked at him the first time when I met him, and I said, Chris, this doesn't look as hard initially. I'm just looking at this, and it looks like I don't know how it will work, but it looks like it can work. And he told me, no, it's not like that. You're not as close as being, say, in Antarctica, where you might have like a team of people sitting around the drill and trying to think that will operate. It's nothing like that. You're flying something that has to have an autonomous behavior. If at all you're trying to send, say, a drill which drills down, and suppose it hits a hard surface, it should be able to understand when it is facing that force and then pull itself back and then reorient itself and do all sorts of things. So drills will complicate the problem. Scoops have been seen to not be very effective, because basically what happened with Phoenix. With Phoenix, they say is a partial success, but the scoop wasn't as useful as they thought it would be. It's a very simple single arm scoop that sat on Phoenix in 2008 when it went there. And basically, because of the problems in its final landing position, it wasn't sitting close enough to a spot where it could collect the samples. Having said that, all these complexities exist and are being addressed at different levels. A pneumatic lander, like the one that I'm talking about, also can face a lot of problems. What happens if it sits on a rock? You're not really having access to any dust, any part of this. And well, the answer is it can. And that's why it's a secondary instrument. It's something that may work, may not work, may get selected, may not get selected. But as a researcher, I was actually interested in understanding how would this pressurized gas interact with the regolith in reduced gravity environment. And the objective for this work, of course, was sample acquisition. But ultimately, when you're trying to do extraction, when you're trying to do in situ resource utilization on Mars or on the Moon or elsewhere, and pneumatics is one of the biggest. The advantages is that you're not having any actuators, you're not carrying that extra mass of different heavy actuators. So one needs to understand at a fundamental level how this solid gas flow would behave, and that's primarily what my objective is.
Siddharth, can you give us some indication about the size? How deep you're going and what's the size of the machine?
Yes, so this is not at all going deep. It's going primarily 5 centimeters into the surface. It's basically going to be sitting on finely loose plane on the surface.
But Curiosity already done that, right? She's gone to 10 centimeters.
Yes, but they're not flying
with a drill.
With a drill.
Yes, they have a drill, and that drill also, like till now, we haven't drilled, I think, more than 2 or 3 inches into the surface. All the rocks that we're drilling is probably just about this much.
So how do you think that sample can represent the entire region?
It cannot. And that's a limitation. And that's where people develop drills which are 1 meter class, and they say 10 meter class, or even 500 centimeter class, and whatever. All those different definitions do exist. But this is trying to be very realistic, trying to send a lander with a hollow tubing inside it, and try to see if you can actually force up some regolith. Honeybee has done some experimental testing, and I'll come to that aspect. But my work was trying to understand how this gas which you're trying to interact with the regolith particles, how best can you optimize that path?
You said this is a secondary instrument. What is the primary objective or mission of this?
So this, like I said, it's just to demonstrate, and it's just a demo. It doesn't have on it right now anything that can acquire samples.
Oh, okay, it's just
but
in the basic design a lander that, as a bonus, can collect.
Correct. That's pretty much what it is. That's pretty much what it is being, say, advertised as. That's what Honeybee Robotics started off with and said that, well, we have all of these other questions that we cannot address, but having had the lander on the surface, these are certain advantages that we can get if we do this. till now we haven't found a very solid reason why we shouldn't be doing this. So that's one way. And
because I mean, once you have collected the regolith in, say, the top part of the landing foot,
yes,
you want actually to look at the regolith, so you have to transport it to an instrument somehow.
yes, and that's also done by the same tubing. We basically use the same pressurized gas which is
Okay,
stored.
and you get it all up to
Yes.
some.
Yes. Alright. So I've given a good background, but I think I should go a bit further because I've got some things to do. So just to give you an idea, the leg of the lander is about 15 inches. You were asking about the size, and about 1 inch diameter of this particular.
Good mix of units there.
So yes, that's what happens when you work in with an Italian professor in the US. But I'm getting back to metric now. So just a quick understanding of how I divided my work. Well, it's a very simple flowchart. On one side, I'm trying to understand the fundamentals, understanding how gas-solid interaction takes place, and how I'm doing that is I'm applying the fundamental approach of first understanding the theory, doing some computations, and then trying to validate part of that computations on one end. And on the other side, I'm trying to make my supervisor at Honeywell Robotics happy, and I'm trying to fulfill certain requirements that
That's the most important part.
Yeah. If you were trying to work with these people, you can't neglect one supervisor. So working with three demons, I used to call them. At some point of time, you start looking at it in that angle, but it didn't start off like that. Well, so it was a space system engineering masters where they want you to look at every topic like a space mission. You need to define yourself. What is it that you're trying to do? What is the need to do whatever you're trying to do? And that need eventually turns into the mission. So the need is you're trying to understand, like I've been saying, the regolith interactions, and that's important because of all the reasons that I spoke about in my previous slides. And how am I going to do that is by using experiments to validate certain computations. And with that I can say that, look, these are the things that can probably optimize the system to a certain level. So that's basically what I call out. I'll also just run through the slide. It's basically a list of all the people who cared about what I'm doing. So you have all the supervisors, and eventually the system will be used by, say, a particular mission. So the design groups would like to know what the outcome is, and eventually people at the university.
So you were based in Delft, Netherlands, right?
I was initially, and then all the work was done in the US. So I was.
So who paid it?
Who paid for?
Travel.
All around the place. Nobody was paying for it initially, but then you find yourself around there. I'll not go through a lot of the academic slides. Well, this was more for my supervisors to know at what levels I was providing them with research reports and things like. So this is the basic workflow diagram which I followed, and the documents which are prepared at every level and that were provided. Not so important for you guys at home. Just a quick understanding of regolith, how it behaves in gas. So this has been studied from an industrial angle because people use pneumatics in industry where you're trying to process certain powders and then you want to move that powder from one point to another point. So how do you do that? So there has been certain work done in this area, solid gas flow, and that was my starting point. And regolith in gas has characteristics just as flow has. You know, when you have different Reynolds number flows, you might, if you have, some of you have fluid mechanics background, you would know that when a flow has a certain velocity and you put an obstacle in the middle of it, you have certain type of vortices, and then when you try to increase the velocity, the types of vortices change, and then the characteristic of the flow changes. So solid particles behave in a very similar way. It's very much a predefined pattern that you try to approach. So there are different ways of looking at it. There's an Eulerian way of looking at it, and there's a Lagrangian way. By Eulerian way, you mean that you put certain pitch stops all around in your zone, and then each of those pitch stops sort of looks at the flow particles in its surroundings and tries to understand. And Lagrangian is when you're trying to send out particles behind these particles, and you're trying to get an overall view of trying to understand how each of those particles are behaving. So just to give you the basic idea of the fluid mechanics of regolith. And this is again a demonstration setup that we prepared at Honeybee Robotics, and very similar to the diagram that I showed you initially. And my work is entirely concentrated over here. So I was trying to understand, coming from a fluid mechanics background, how is it that one can design these ports over here? Well, they, at Honeybee Robotics, did not have a very good idea, so they just bluntly put these rough poles all around and thought that they'll just force a gas and it will bring up samples. But I said, yes, you have shown it happen in your setup, but can you optimize this, and how have you achieved these particular distributions of these ports? And that was my work. So I was trying to model the flow as it was interacting right at this point with the regolith, and that was my entire work of my thesis. Ultimately, there were other areas that I would like to have worked on.
One question: did you plan to have the tube extended before the landing, or land and?
Yes, good question. So yeah, after you land, there's an actuator which actually forces the. Yes. So there were few areas that were that I had delineated and said that these are things that one needs to investigate. The first of them was the point of interaction. As soon as the gas comes out and then it interacts with the regolith, that was the first point. Another point that I had put forth was there are so many things that one needs to understand. Whenever you're trying to have a pipe and you're trying to put a gas through it, that itself creates a lot of different flow scenarios as you reach near the wall or away from the wall. And when you put regolith through it, so it's a multi-phase flow, it's not a single-phase flow. And that itself creates a lot of problems, because you might have problems where the regolith actually collects in one area and blocks the entire flow as well. So one needs to understand all these particular things. And another thing that I didn't mention is that regolith is very abrasive, especially on the moon. If at all it impinges on the internal surfaces, it can damage and it can sometimes rupture them because they're really sharp. And especially on the moon where there's no atmosphere, there hasn't been any rounding of these particular grain particles. They're very sharp little particles. And also on Mars, you expect to have this. So it becomes important to understand or to be able to force. So if you have, say, a 90-degree pipe, you want to ensure that your regolith is flowing an optimal path through that particular pipe and it is not being stored and all of those things. So that was another area which I didn't focus on, but primarily these were two areas, and there were other areas where eventually when your regolith tries to reach the sample canister, you use a cyclone separator to separate out the gas and then collect the samples. So that was another area of research that could have been focused on. And all of these areas are important not just for this particular lander, but in general, one needs to understand how you use pneumatics to transport regolith particles.
Another question: have you maybe looked at how to say because I mean, depending on how deep or how much the regolith fills inside the tube, the holes where you plan to have the gas flowing out might be blocked by regolith, or not. How to say, be completely empty so that the gas flows empty out.
Yes, I did. That was one of my objectives for my experiment, was to find an optimal depth to which you need to insert this particular pipe. So that was.
Did you plan to have sensors on the inside to validate actually that the level of regolith is what you need, or is it more?
It was more mechanical. So my focus was more on. So I'll get to what I actually did. I modified the distribution of these ports, and I tried to understand, or this was my hypothesis, that if you incorporate a swirl motion within the particular pipe, so instead of having gas ports which are just looking into the radius, if you actually have them at certain angles and at different angles, and not just in the swirl direction but also in upwards and downwards direction, how would that affect the final regolith?
Okay, so to basically have
yes, a swirl motion. Yes, and to see if that eventually, and to find out whether it affects it or not, you'll have to wait for the last slide. Yeah, so that is this slide over here. So this is what was my basic control volume geometry that I was looking at. So you basically have a side view of the lander foot leg over here, on the top and on the bottom. And as you can see over here, these red ports are basically where the gas is getting inside, and this is the common space for the mixed flow to move up. And this is the top view, which gives you an idea of the angle. Now you can't see the angle over here, of course, but you can see it over here on the side view. So over here the theta is about 45 degrees angle, and over here the theta is also 45 degrees. So it is pointing down, and it is also having a swirl motion. So alpha is 45. So I just defined two different angles, and I kept in front of me a set of candidate geometries that I modeled, and then I tested them. So I used ANSYS Fluent package for doing the modeling part, and what you see over here is basically a comparison of two different candidate nozzles, and one of them is having 0 degrees, so it's a control case, basically what we started off with, where you don't have any angles, you're just having flow coming in, and the other one is having a swirl angle of 45 degrees, and these are basically time stepped at I think 10 milliseconds or so, and you're basically seeing, so this is volume fraction, so that's basically the red says that it is entirely regolith, and the blue says that it is just gas, and this is a qualitative comparison for ease of viewing, for you to understand that how swirl actually increases the speed at which the regolith actually was flowing through and passing through these particular tubes, between these two tubes. So very quickly you can see that the rate at which the regolith was picked up and also which moved forward. That is the first thing that comes across, that the volume fraction progression is faster when you have a swirl angle. The other thing, which is not so apparent, but you can sort of make out from this particular contour, time step contour, is the distribution as well. So a much more uniform distribution of regolith with the gas was seen with the swirl case, as compared to without any swirl. And as you can see over here, where you see sort of lumps of regolith which are moving forward, as compared to in the case of the swirl, where it is much more uniform.
The particle size is important.
Yes, it is. And that's something which I did not completely incorporate. I used an average size of 30 micrometers. But that...
Why 30?
That is from the Mojave simulant. So from the simulant which I had for my experimental work, I just used the same. That itself is not seen to have average 30, but this was for ease of modeling, opposite to anything else.
Do you plan to use maybe a regolith that has, say, a throughout distribution of particle sizes?
Yes, so the simulant that I use for my experiments is called Mars Mojave simulant. It's a natural Martian simulant, right? So it has a natural distribution in itself.
Okay.
Having said that, it is important to understand how these regular particle diameters affect the final distribution as well. And that is something which I haven't done up until now, but that is a major design critical element that has to be done. So these are the first top left and right graphs basically give you volume fraction distributions. So what this is doing is that the same, if you're looking at the side view of your sample tube, so from one end to the other end, it gives you the sort of distribution of the sand particles. And it was seen that the swirl assisted flow led to a much more wider distribution of the volume fraction as compared to the case when there was no swirl. So this is beneficial for us. It allows more regolith to move per, say, square millimeter of your particular pipe length, and eventually leads to a higher capture of regolith. Another thing is the eddy viscosity of the regolith in itself. So basically what one tries to do with swirl is you try to incorporate a smooth transition. You don't want a lot of turbulence taking place at the bottom. You are incorporating a swirl, that is turbulence, but in itself you're not losing out on a lot of momentum that is coming out from the gas. It's an effective momentum transition from the gas into the regolith and then just carrying it and taking forward. And that's what we're seeing from lower eddy viscosity values for regolith as compared to the non-controlled case. So this gave a certain set of observations from the modeling, and eventually that led me to select 3 particular designs. on the basis of the performance of these particular nozzles to do experimental tests. And I designed a small lander foot leg, which didn't look at all like this particular lander foot leg, but basically this is the one that Honeybee had, and if you explore it, it is containing all of these different components. And this is the important one because this has the holes. So it's basically, this is having two walls, so basically the flow is coming in and eventually being forced out into this particular main juncture. So I made this particular component for the experimental tests, and each of these, so I had 3 of these nozzles that I fabricated, and each of these nozzles was having a different orientation to compare and validate the model's works.
So the two angles, swirl and down and upwards.
Yes. So one of them was the control case. One of them was with a swirl, and one of them was with the angles, upward, downward.
And the third?
Those were the 3. The first was control. So control is there's no angle, no swirl.
Radial.
Yeah. So
how about the combination of swirl and?
I wish I had funding to get more nozzles fabricated.
Maybe
But
3D printing?
yes, so all of these were 3D printed, and the ones that I selected were on the basis of the maximum, the model predictions from those. And of course, if I went lower, I would have got a much more better distribution of how.
So the results of the swirl and downward were not that good in the model?
They were, and that's why they were. Oh, you mean with the swirl and downward?
Combined.
No, they weren't. So it was only with the swirl and then downward and then just clockwise. These 3 cases. And basic simple setup where, of course, I cannot model gravity on Earth. It has been done. People have flown parabolic flights where they have actually looked at how pneumatic systems work in bouts of reduced gravity. But I didn't have that luxury of doing that. But I was able to understand how my particular shapes, so it wasn't really an Earth versus Mars comparison, it was just a design comparison where you're trying to understand how different gas flows can affect the final regolith distribution.
Did you try to model the reduced gravity? That should.
I did, but I didn't have any experiments to show, so I can't publish that work because whatever work I have, I can.
But if you predict what happens with Earth's gravity,
I did,
and then do an experiment that proves that, then you can use the same model with Mars's gravity and Mars's atmospheric pressure.
Yes. So for this particular gas interaction zone, I didn't see any difference in Earth and Mars. And over here, I'm just talking about the interaction between the gas and regolith because the time interval is so short for gravity to affect. The buoyancy is not coming into play at all. It's only the pressure forces which are higher than this. But having said that, when you're trying to transport them over longer distances, over longer time intervals, that's when it can work in effect. And that was also seen by the parabolic flights which Honeybee Robotics did, that gravity was not affecting. So basically, the cases with the swirl assisted and angle were better than the control radial case, and that was, so I had 2 different regolith candidates as well. I was using JSC 1A, which is basically lunar regolith, and I was using Mars Mojave simulant as well.
What's the difference between the 2?
Mars Mojave simulant is of course more like what we would expect from Mars. It's much more coarser. It's much more coarser, yeah. And JSC is very fine. It's grey in color and it's very fine. So I was able to capture more of the lunar simulant as compared to the Martian simulant for the same particular.
Because it's finer, probably.
Yes, because it was able to get a much more uniform distribution.
What is the composition of regolith in your army? Is it bentonite or calcite or carbonite? What sort of?
I forget the elements. I'm looking at that. It's fairly standard, but it just slips my mind. Yes, so yeah, so here you can basically see the comparison between the experiments where I was able to get different pressure pulses. So I was pulsing different pressure values, and this is only between 0 and 1 bar. So within 1 bar of gas pressure itself, I was able to collect a certain amount of regolith
Is
samples.
Is that the maximum?
Not really. This is just to show that within 1 bar itself that we were able to collect certain samples
Okay.
on board the lander.
Do you know what's the typical pressure of pressurized gold gas?
So there are different numbers that people say. It all depends on what the final usage is. I was told about 20 psi. Roughly, I don't know how much that would convert into bars, but yeah. But for my experimental, this was a constraint also for my experiments, that I wasn't using 20 bar, I was only using just 1 bar of pressure to these. And I have also put in some photographic captures from the one which are, I think, not very clear. But basically, the material that we used for the 3D printing was translucent. So that was done so that one was able to actually see the distribution of regolith as compared to a lighter background. And these are the images on the left of these photographs are basically density isocontours from the model. And they basically tell us that there was a uniform propagation of regolith as it was going up the tube. And given that this could have been done in a much more better way, where one can actually do a lot of use PIV techniques, non-interference techniques, to photograph regolith as it is passing through gas, and that could be one work that could be taken up to better gauge. So my experimental validation was on the basis of the collection of the regolith. Another important thing that can be done is the distribution of regolith, how it is taking place. And I was able to get some photographs and be able to compare them with my CFD model and say that this is basically what the flow looks like in the model, and this is what one is getting from the experiments. So the final conclusions of the work were that yes, swirl and angle assisted flows eventually do lead to better capture of regolith. This is being looked into now in a much more better way, whereas we are trying to do some more tests within a vacuum chamber in Pasadena and try to see if we can achieve the values which my model had got for different temperature and pressure environments. And the optimum depth to which the lander foot leg needs to be penetrated is about 5 centimeters for this particular case. That is another thing that I was able to get. I was able to measure it up and down and see at what level I was getting the optimum value.
Maybe a question.
Go ahead.
This penetration depth, what is important, I reckon, is how much regolith you have in the tube at the end. Is there a way to control that, or will you just, like, based on assumptions on the soil you will encounter, penetrate to that depth? Because, well, you may, if, how to say, the grains are finer or thicker where you land than you suppose, you might get more or less of regolith.
Yes.
And basically, as you said, I think this is very important and can lead to no acquisition at all.
Yes. Yeah, it can be done, but within this particular system, it isn't being looked into. One is trying to send a lander foot leg design in such a way that it is ready to be able to work with different regolith sizes and diameters. That is a luxury that we do not have. It can be done. Like, you can actually optimize that at that point as well, where you're trying to, depending on, say, the softness of the regolith, you only insert it to the point that you think that you'll be able to lift up.
Okay, so you measure first the softness of the regolith before deciding on how deep you want to insert.
Yes, yes. So for every different, and that's pretty physical in that sense, that you already know for a certain distribution of regolith, if you try to throw a particular mass, how much will it actually sink inside it. So those are things that can be tested and already one can achieve.
Or you can, if you have an actuator actually,
yes,
you can just, it's not working, I can take it out,
probably take it
or
out.
put it in.
Yes, yeah, but in the real world, all of these ideas of what I went to Chris with, and he's like, well, you know, I've been in this business for 20 years, this doesn't work. All they want is, and that's the most surprising thing that I found at NASA Ames. There were guys who had brilliant designs, they had built hardware, and eventually what flies Curiosity has a drill that you can buy from a local hardware store. That's the reality. They don't want to take any chances. So there goes away all your research and all your years of operations. But ultimately, yes, it's like I said, all of this work is not just for this particular lander to fly to Mars and get samples. It is to understand how regoliths would behave in such environments. And by doing this particular subsystem development, I was able to achieve certain understandings. Some of my hypotheses were met because of this work, and that was more important. And one can take this technology, and we are doing that, and we are focusing towards asteroids, towards human-assisted sample acquisition, to have some sort of instruments that the astronauts can actually carry at some point of time, and instead to having to scoop over, you can just puff it all around, and then you can just capture the samples inside. So pneumatics is something that hasn't been looked into deep enough and should. So with that I will conclude.